Hello, my name is Padmavati Iyer. I'm going to present on the topic paging, a fundamental tool of memory management.
So let's look at why we need paging, or more particularly, what were the disadvantages in traditional memory management schemes. Traditional memory management schemes that involve memory partitioning, like fixed size partitioning and variable size partitioning, created memory wastage due to internal fragmentation and external fragmentation. Fixed size partitioning caused internal fragmentation because the size of a process might be much smaller than the size of the partition allocated, due to which a hole is created within a partition. On the other hand, variable size partitioning causes memory wastage due to external fragmentation. Even though the size of the partition is dynamically allocated based on the size of the process, this scheme of memory management quickly litters the main memory with blocks that are too small to satisfy any memory requests. Hence, paging solves the issues inherent in these traditional memory management schemes. So let's look at how paging addresses these issues. The basic mechanism of paging is quite straightforward. The main memory is divided into small fixed-size chunks called frames or page frames, and the process on disk is divided into small fixed-size chunks called pages, whose size is same as the size of the frames in main memory. Whenever a process is brought into memory from disk, all its pages are loaded into available frames in memory. At any point of time, the operating system maintains a free frame list, which is a list of all the free frames or the unoccupied frames in main memory that are available for processes. Now let's look at some of the advantages and downsides of this scheme of memory management. Paging offers a number of advantages, the principal one being preclusion of external fragmentation. Since the partitions created are of fixed size, so paging does not give way to external fragmentation. The second significant advantage of paging is that pages of a process need not be allocated to contiguous frames in main memory. Now let's look at some of the downsides of paging. Paging can cause memory wastage due to internal fragmentation when the last page of a process occupies only a fraction of the total page size. Nevertheless, since the size of the partitions is small, so the degree of memory wastage caused by internal fragmentation is reduced. Let's look at an example of how the paging actually operates. This will make the paging operation more clear. The figure shows the structure of memory and page tables for two processes A and B and a free frame list. The free frame list contains all the available frames in main memory that can be occupied by next available process. The page table of a process contains one entry for each page within that process and is indexed by the process page number. Each page of a process is associated with a frame number, which indicates the frame location of that page in main memory. For example, in the figure given, process B has two pages indexed by page 0 and page 1. Their page 0 resides in frame 3 and page 1 resides in frame 4, as is depicted in the main memory structure. And similarly for process A. Now, let's assume that at some point in time, both process A and B are clogged. So the operating system needs to bring in a new process C to prevent CPU idle time. So now the new available process C contains 3 pages indexed by page 0, page 1 and page 2. An important advantage in paging is that the 3 pages of a process need not be allocated contiguously in main memory. The 3 pages of process C can occupy any 3 available memory frames. As depicted in the figure, process C indexed by page 0, page 1 and page 2 correspondingly occupies frame 2, frame 5 and frame 6 depicted in the main memory structure. Also, observe that the free frame list now contains only one entry since there is only one available frame in main memory for next process. The next aspect we need to consider in paging is how the processor dynamically translates a logical address to physical address at runtime using the page tables of a process. Now, before proceeding, we need to note an important point. The size of the page and the frames are usually taken as power of 2 because of two reasons. First, this makes the hardware implementation of dynamic address translation from logical address to physical address easier. The second reason is that it makes it easier to understand that the relative address which is defined from the beginning of a program and the logical address which is defined based on page number and offset are equivalent. For these two reasons, the page sizes and hence the frame sizes are usually taken as power of 2. Now let's look at the procedure of how the processor uses the page tables to translate logical addresses to physical addresses. Logical addresses found within a program comprise of page number and offset within the page for a referenced byte, and the physical addresses are actual memory addresses of the referenced byte which comprise of the frame number and the offset. Okay, now let's see if given a logical address comprising of a page number and an offset, how can the processor retrieve the physical address for the referenced byte? This page number can be used to retrieve the frame number from the page table that indicates the frame location where the current page resides in memory. After retrieving the frame number from the page table, the physical address of the referenced byte can be calculated by appending the offset to the retrieved frame number. Now, let's look at an example that will make this logical to physical address translation more clear. In this example, we assume that all the addresses are 16 bits. Suppose the processor encounters a 16-bit logical address within a program. Given the page size and the frame size is 1K, which is 2 to the power 10, so the offset size will be 10 bits. Hence, in a 16-bit logical address, the rightmost 10 bits indicate the offset and the leftmost 6 bits indicate the page number. In the example given, the referenced byte resides in page number 2 and offset 11 within page number 2. Now, the processor uses the page table of the current process to retrieve the record, or more particularly the frame location or the frame number associated with page number 2. Now, this page number can be used to retrieve the frame number from the page table. In the given example, page number 2 is associated with frame number 000100, which is frame 4. So, the starting physical address of our required frame can be calculated as 4, which is the frame number, into 2 to the power 10, where 10 is the offset size. And the physical address of our referenced byte can be calculated by adding the offset to the starting physical address of our required frame. However, this calculation can be made easy by appending the offset, that is 11 or 000001011 in binary, to our frame number, which is 000100, or frame number 4, thus giving the 16-bit physical address of our referenced byte. So this example shows how page tables can be used to dynamically translate 16-bit logical address to 16-bit physical address at runtime. So this presentation was about paging and its role in memory management. In summary, we covered the following points in this presentation: need for paging in memory management and the disadvantages inherent in traditional memory management schemes that involve memory partitioning. Next, we discussed about the paging mechanism and structure of page tables and how they link the pages of process on disk to frames in main memory. Later, we discussed how the processor uses the page tables of a process to dynamically translate a logical address comprising of page number and offset to physical address comprising of frame number and offset for a referenced byte. Also, we discussed some advantages and downsides of paging.
Hope you liked watching the video. Thank you so much.